Hello friends, welcome back to the course Basics of Mechanical Engineering 1. Professor Ramkumar has covered a lot of topics regarding the basics in mechanical engineering, starting from units and dimensions. We talked about laws of motion, scalars and vectors, all the basic elements which are employed in mechanical engineering applications. And we also covered the topics in solid mechanics. We covered majorly the mechanical properties such as stress, strain, residual stresses, and we talked about stress strain curve, we talked about principal stresses, and I think in principal stresses I have also covered tutorial, which was tutorial 1 and 2. This tutorial 3 would be covering remaining part of the solid mechanics, that is hardness, toughness, impact, creep as one of the sets. Then we will talk about static and fatigue loading and critical loads. Some numerical problems would also be discussed upon these. Then stresses in cylinders and spheres and also buckling of columns would be covered, and then we will also try to see some problem statements on how to draw Mohr circle to understand or find the forces acting upon any body in different directions. Let me start it from the hardness, toughness, impact and creep. The definition of hardness, if you call, it is resistance of a material to deformation. Just to recall quickly, so particularly permanent deformation is there, scratching is there, cutting is there, abrasion is there. Resistance to any permanent deformation is hardness. The common hardness tests which are there in the laboratories are Brinell, Rockwell, Vickers hardness tests, and BHN, that is Brinell's hardness number, is given by 2F by pi d minus square root of the difference between the two diameters. I will come to the notations and everything in the forthcoming slides. So, also creep, it is time dependent permanent deformation under the constant load and stretch. This was discussed, like you put clothes for a dry on a metal wire, the metal wire while having the load for the whole day, the weight of the clothes is not that heavy, but the load is there for 8 hours, and this 8 hours each day for 6 months you will see the wire getting loosened. So, that is creep load is happening there. So, creep rate is epsilon dot is A sigma power n, then the negative exponential of q by RNT. So, where epsilon naught is creep rate, sigma is applied stress, q is activation energy, r is gas constant, T is absolute temperature. So, let me try to see some numerical statements and we keep on discussing the relationships there. A steel sample is subjected to Brinell hardness test using a 10 millimeter diameter ball and a load of 300 kgf. The diameter of indentation is 4 millimeter. Calculate Brinell hardness number. I will also discuss in the next week the laboratory demonstrations on the different tests which are there in solid mechanics, the tensile test, compression test, and also we will try to talk about test in hardness. And there also we will see how do we calculate, how do we actually conduct the test to understand the Brinell hardness or other hardness numbers, and we will see how do the relations hold good. So, here BHN is given. So, I have capital D is 10 millimeter. What is this? The ball diameter, and small d is 4 millimeter. Using the relation here, so this is ball dia, this is indenter dia, and this is force, the load that is being applied. Now, we have this relation BHN is equal to 2F by pi d into the difference of d from the difference of the square root of the squares of the diameters. So, which is BHN is equal to 2F by pi d into d minus under root of d square minus small d square. So, let us put all the values here. I have the value of the load as 3000 kgf, kilogram force. This is the value of F. So, I have 2 into 3000 by pi into 10 into 10 minus under root of 10 square minus 4 square. This is equal to 2 into 3000 is 6000 by pi into 10 multiplied by 10 minus 10 square is 100, 4 square is 16, 100 minus 16 is 84, 10 minus under root of 84. This we have to use calculator to find the values. If you try to find the value, this becomes 6000 by pi into 10 into 0.83, where the Brinell hardness number is 230 BHN. Exact BHN, if you calculate, is actually 228.76. So, this is how do we calculate the BHN value. We also try to see the test on different materials. This is a steel sample it is telling, and BHN number has come this value. Now, another problem statement that is given regarding toughness. A notch specimen is subjected to an impact test and the energy absorbed is 20 joules. The cross-sectional area of the notch is 0.01 meter square. Calculate the impact toughness. Impact toughness is this is equal to energy absorbed by cross-sectional area, right. So, what have we given? We have been given the energy absorbed is equal to 20 joules, and we have cross-sectional area is equal to 0.01 meter square. No requirement of the change of the units. It is directly I have impact toughness is equal to 20 by 0.01. It is joule and in meters. Everything is in SI. So, this becomes 2000 joules per meter square. So, direct. Similarly, let us try to see another toughness test for tensile load. So, there is another problem statement where tensile load is there. You see here, a tensile load is there with a force of 10,000 Newton. A cylindrical specimen of diameter 10 meter is subjected to this load. So, we need to calculate the stress and determine the material's toughness if area under the stress strain curve is 300 megapascal. So, this area under stress strain curve that was also discussed by Professor Ramkumar. So, we have stress is equal to force per unit area. So, force is given here 10,000 Newton SI units, area under stress curve is 300 megapascal. So, megapascal could be converted into the SI units, and cross section area we can calculate using the diameter. So, we have been given diameter is equal to 10 millimeter, which implies area A is equal to pi d by 2 square, which is equal to pi into 10 mm is, in meters if I say it is 0.01 meter by 2. This is equal to 7.854 into 10 raised to power minus 5 meter square. So, this is my area. Now, I have to find the stress. Stress sigma is equal to F by A, it is equal to 10,000 by this area 7.854 into 10 raised to power minus 5. So, this is almost equal to 127.4 megapascal. Now, I leave the toughness part to you. It has been given that the area under stress strain curve is 300 megapascal. You calculate it, I will give you the answer. That answer would be there in the lecture notes, but you still try to calculate it and come up with the answer. Let us see how do you go. So, similarly, let us do another numerical in BHN. It is very similar to the problem statement we did above. So, here BHN number is to be determined when ball die is given, indenter die is given and force is given. I have a similar numerical for you to take it as a home assignment. The load is given 50,000 Newton, right. Here F is equal to 50,000 Newton and BHN is given now. BHN is equal to 150. We have also been given the diameter of ball. Diameter of ball is capital D. This is equal to 10 millimeter. What is required or what is asked? Calculate the diameter of indentation. Small d is asked, which means again BHN is equal to 2F by pi d into d minus d square by small d square. We need to calculate the value of small d. Just calculate this value, you will also get the answer in the slides. So, this is directly because this is square of it, you have to take under root, BHN is given, F is given, capital D is given. Calculate the value of small d. This is again a home assignment. Just to solidify our calculations once again, I will do one more numerical in this direction. BHN is given, load is given 5000 kgf and 10 meter diameter of ball is there and dia of indenter is 3 millimeter. Quickly our BHN is equal to 2 into the force, that is 5000, right. F is equal to 5000, capital D is equal to 10 and small d is equal to 3. These are in mm and this force is in kg force, kilogram force. So, this by pi into 10 into 10 minus square root of 10 square minus 3 square. So, this value is coming to be 10,000 by pi into 10 into 10 minus, this is 10 square is 100, 3 square is 9, 100 minus 9 is 91, under root of 91. This is equal to 10,000 by 14.45, which is equal to 691.97 BHN. So, this was majorly about the hardness test. Let me also take one more numerical on impact test. and we will try to see toughness, or we will try to find impact energy per unit area when it is given that in a Charpy impact test it absorbs 80 joules of energy before fracturing. The cross sectional area of the notch is 16 millimeter squares. Now here cross section is 16 millimeter squares. So we need to convert this into SI units, that is meters. Let us first put the energy absorbed. This is equal to 80 joules. Then we have cross sectional area is equal to 16 millimeter square, which is equal to 16 here 10 raised to power minus 3 meter square, which is equal to 16 into 10 raised to power minus 6 meter square. So impact energy per unit area. This is what is asked, impact energy per unit area. So this is equal to energy absorbed by cross sectional area. This is energy absorbed per unit cross sectional area. This is equal to 80 by 16 into 10 raised to power minus 6. This is equal to 80 by 16 is 5, and 10 raised to power minus 6 goes above as 10 raised to power plus 6 or 10 to the power 6 itself. This is 5 into 10 to the power 6 joules per meter square. This is so direct. I will discuss more about hardness, toughness, impact when I will take the laboratory demonstrations. Now let us move to the static and fatigue loading. So just to recall the general relationships that we have, this is stress when force is acting in two opposite directions, you see, or for the force could also be applied in the same direction, that is compression. So the stress here is force per unit area, where area is given here. So if it is inclined, the A star area becomes area by cos phi. Phi is the angle at which this is breaking. So this is stress that is there, the force in different directions. If it's the direction of force, exactly force opposite to the direction of the force is normal force N. So strain is change in length per unit original length. So this is the original length L, small l here, and this is the change in length delta L. So the total force here is F acting in both the directions, in the left and the right directions. So force per unit area is our stress as it is given. Now strain could also be there for two conditions, undeformed bar and deformed bar. For undeformed bar, you should say the x has changed, or the strain is there, and dx is the increase in length. When the bar is also deformed, this is deformation value u. So when u or beyond u, it is u plus du. Here the total change in length becomes dx plus u plus du minus u, right. Similarly, to recall the concepts on tensile loading, you see the tensile loading, the loads are acting in different directions. One in, you call it negative direction, another in positive direction. So there are resisting forces oppositely acting. Suppose at this point the force is acting. This is the plane at which forces are acting, plane xx. So on the xx plane there are resisting forces R, right, and also forces opposite to the forces acting upon the positive axis or right axis. So that is again force R. So here you see a combined figure where load is being applied into different directions and there are resisting forces. So this resisting force gives me the value of stress, that is a resisting force per unit cross section area, which is equivalent to my tensile load per unit area. So this stress, tensile stress is P by A. Also strain is again increase in length by original length, that is dl by L. In the case of the compressive load, the forces are acting in the same directions, the things are being compressed. So, here also the force is acting in negative direction, here also it is in negative direction. The resisting force is also in the same direction here in this case. Here the load is acting in this direction, in figure C the resisting force is in the opposite direction. But anyway, whatever the resisting force is, here in case of pull it becomes push, but still stress is same, resisting force per unit area, that is push per unit area, that is P by A, and strain is also same, that is change in length by original length. However, here the change is decrease in length. This is the difference between compressive and the tensile forces. Now comes the shear stress. You see here the force is acting in this direction, this is a rivet, this rivet is subjected to a load P in the negative and positive direction, and this is the plane where shear could happen. So, at a shear plane the shear stress, this is equal to tau, which is equal to again resistance force per unit area. So, here if phi is there an angle, obviously again the area will turn to A by cos phi, and similarly the changes could happen. So, this again I could put here load per unit length. Now, let us try to recall the Hooke's-Clarke states that the Young modulus is stress per unit strain, for which the relation holds good like this, right. So, because stress is proportional to strain, so stress is equal to Young modulus into strain. The Young modulus is the ratio of stress by strain. So, that is we have already discussed for steel it is from 80 to 100, for wrought iron from 80 to 90 and so on, different materials are given here. For timber or wood it is very low, it is 10. The Young modulus, that is the more the Young modulus is, more strength the material has. So, next is shear modulus or modulus of rigidity. So, it has been found experimentally that within elastic media the shear stress is directly proportional to shear strain. We have shear stress proportional to shear strain, tau is shear stress, phi is shear strain. Again similar to the proportionality relation here for sigma and epsilon, we have tau is equal to C into phi, which means the modulus of rigidity or shear modulus C is equal to tau by phi. So, C is constant of proportionality, also known as shear modulus or modulus of rigidity. It is also denoted by N or G by certain authors or in certain books you will find it in this way. Now, again for shear modulus there are tables available, those tables will be shown you when we will try to show you the laboratory demonstrations. Let me try to come to a problem statement here. The ultimate stress for a hollow steel column which carries an axial load of 1.9 mega Newton is 480 newtons per millimeter square. If the external diameter of column is 200 millimeter, internal diameter take factor of safety as 4. So, let us try to use the relationships that we have learnt in the lectures. Let me put down the values which are given. We have been given that ultimate stress is equal to 480 Newton per millimeter square. It says axial load is there. What is the load? P, it is axial load. This is equal to 1.9 mega Newton, or I call it twice 1 or I can put it as 1.9 into 10 raised to power 6 newtons, right. Other values which are given is the diameter of the column, the external dia. External dia, that is capital D, is equal to 200 millimeter. and internal dia is asked, right. Now, we know the area of cross section of the column, area is equal to pi by 4 into the difference between the diameters. So, which is equal to pi by 4, the capital D value is given 200 square minus D square, right. This is my area. Factor of safety is also given 4. I will put it here, factor of safety is equal to 4. Now, factor of safety relation that is discussed in the last lecture is ultimate stress per unit working stress. You call it working stress or you call it permissible stress. This is my factor of safety, which means factor of safety value is 4. This is equal to 480, ultimate stress value is given, and working stress we have to put it here. So, this gives me the value of working stress, that is sigma. This implies sigma is equal to 480 by 4, that is 120 Newton per millimeter square. We have gotten the value of sigma now, that is my stress, which is equal to load per unit area, right, which means this value 120 is equal to load is 1.9 into 10 raised to power 6 newtons per unit area is pi by 4. You call it as equation 1. I will write it as from 1, this area value I put it as pi by 4 200 square minus d square. Now, there is only one unknown here and we can definitely find this value if you wish me to calculate it. So, we will calculate it as pi by 4 into 200 square minus d square is equal to 1.9 into 10 raised to power 6 by 120. So, which means 200 square I will put it as 40,000 minus d square is equal to 1.9 into 10 raised to power 6. 4 goes up, pi comes down, 120, which means my d square is equal to 40,000 minus the above value, and this value turns out to be 20159.6, which means the value of D or the internal dia of the column calculated is 140.85. What are the units? Everything is here in SI units. So, this is millimeters. This is the solution, right. So, this is another numerical problem in the similar direction where we have lateral strain, where we have the Young's modulus given, determine the change in length, breadth, thickness of a steel bar. It is length, breadth, thickness, all the parameters are to be determined here. So, before load, this bar was 4 meters long, 30 millimeter wide and 20 millimeter thick, and actual pull if it is there, definitely to recall, compressive was push, the word push was here, and tensile was pull. So, here it is pull here, tensile load problem statement. Right. Now, in direction of its length is that it is telling the pull is in the direction of its length and the load is 30 kilonewton. we have been given the value of the Young's modulus, that is E is equal to 2 into 10 to the power 5 newtons per millimeter square, and Poisson ratio is also given. Similar problems were also solved in the tutorial 2, but this is now asking length, breadth, thickness, everything is to be determined. The change in all the 3 dimensions is to be determined. Let us try to put down the given values. Length L is equal to 4 meter. Then we have breadth, I will put it as small b, this is equal to 30 millimeters, and thickness, I will put it as small t, is equal to 20 millimeters. Also we have been given the pull value, that is the load. Load is equal to 30 kilonewton. Load P is equal to 30 kilonewton, or we can call it as 30 into 10 raised to power 3, that is 30,000 newtons, and value of the Young's modulus and Poisson ratio is given. So, from the length, breadth and thickness, let us try to calculate the area. Area of cross section, this is equal to breadth into thickness, that is equal to 30 into 20, which is equal to 600, both of them are in millimeters, so it is 600 millimeters square. So, axial pull is given already, and we have also been given the Young's modulus, 210 to the power 5 Poisson ratio. Now, let me try to calculate strain in the direction of load, that is longitudinal strain. Right, this is equal to, because we know E is equal to stress by strain. So, we will put longitudinal strain is equal to stress by E. Here value of stress or load, that is load by area. Here stress is equal to load by area. So, I will put load by area into E. So, these values are given to me. Load is what? 30,000. Area is what? We have just calculated 600, and value of E is also given, 2 into 10 raised to the power 5. This gives me the value of the longitudinal strain as 0.00025. This becomes our starting point. We have gotten the value of longitudinal strain. To find the values of delta L, delta B and delta T. These are asked change in length, change in breadth and change in thickness. Now, I have gotten the value of longitudinal strain. What is longitudinal strain? Put it as part A. Longitudinal strain is equal to change in length delta L by L, which is equal to 0.00025. Therefore, delta L is equal to length into the value of strain, which is equal to, the length is given already 4 meters. 4 meters means 4000 millimeters into 0.00025, which gives me the value of delta L as 25 into 4 is 100, and there is decimal place after the 5 numbers here. So, this gives me 1.0 millimeter. This is answer 1, right? I will call it as 1, 2, 3. B. For lateral strain, let us now see the Poisson ratio. Poisson ratio is given. What is Poisson ratio? Poisson's ratio is equal to lateral strain over longitudinal strain. So, Poisson ratio is given 0.3, lateral strain is a unknown quantity here, a longitudinal strain we have calculated here already 0.00025. This gives me lateral strain value as 0.3 into this, which is 25 into 3 is 75. Another decimal place is increased 0.00075. Now, this lateral strain is also equal to change in breadth per unit breadth. Breadth we know now. This is equal to change in breadth by value of breadth is 30 millimeters, which gives me the change in breadth value as 30 into 0.000075. This is equal to 75 into 3 is to 25. So, this becomes 0.00225 millimeters. This is answer 2. Third part. Similarly, we know change in thickness per unit thickness is our lateral strain, right? Which means change in thickness is equal to lateral strain, that is change in thickness is equal to thickness into lateral strain. Thickness value is 20 mm into lateral strain value 0.00075. This gives me change in thickness value as 20 into this. So, 75 into 2 is 150. This gives me 0.0015 millimeters as value of the change in thickness. So, I have gotten the 3 values. So, what is the physical change in the dimensions of the given bar are now determined. This was an interesting problem. There is another problem, very simple, similar to the one that we have been doing in this tutorial and the previous tutorial. A steel rod is 2 meters long and 50 millimeters in diameter. An axial pull of 100 kilonewton is suddenly applied to the rod. Calculate the instantaneous stress induced and also the instantaneous elongation produced in the rod. B is given. Here you have been given length is equal to 2 meters. If you convert it into millimeters, so this is equal to 2000 millimeters. Also, you have been given the dia small d is equal to 50 millimeters. We have been given the axial pull, that is the value of P is equal to 100 kilonewton or 100 into 10 raised to power 3 Newton. We need to find the instantaneous stress, that is, we need to find the value of sigma. We have to find the value of the elongation, that is delta L. These two we need to know. How would you go about? I am not solving it for you. You will find this solved in the lecture notes. Then how would you proceed on it? Obviously, the way you did it in the previous numerical, we will first find the area, right? Finding the area, then let to know using load per unit area and given the value of the Young's modulus, you will find the value of sigma, right? From the value of sigma, once you have known, then this is again load per unit area. Because the load is applied suddenly, a catch in this numerical that you need to take care about is here stress is equal to 2 times load per unit area. Because the load is suddenly applied, it is applied in the both the directions. So, this is very important here. I will mark it in a different color. This is for sudden load, or this is a keyword, suddenly applied load. Because otherwise all the values that you get would be half of the value which actually should be. So, here the stress is doubled here because the sudden load is there. So, this you will solve, try to find the answer and compare it with what you get in your lecture notes. Next numerical is talking about a shaft that is transmitting 100 kilowatts at 160 rpm. Now, we are talking about shaft, that means a torque would come. Find a suitable diameter of the shaft. If maximum torque transmitted exceeds the mean by 25%, take minimum allowable shear stress as 70 megapascal. So, we are talking about shear stress because shear stress is there. Now, we have the value 70 megapascal as my value of tau. Or you call it megapascal, or you call it 70 newtons per millimeters square, the value of tau. Now, it says transmitting 100 kilowatts at 160 rpm. So, power here is power P is equal to 100 kilowatts, and we have the frequency, you call it omega or you call it n. I will call it frequency of rotation, or you call it rotation per minute, rpm. This is 160 rpm, and it says the torque transmitted exceeds the mean by 25%. Now, T max, that is the maximum torque, is equal to mean torque plus 25% of mean torque, which is equal to T mean plus 0.25 of T mean, which gives me T maximum is equal to 1.25 of T mean. So, let us try to find the solution that they have asked the suitable diameter of the shaft. This is the question. What is being asked here? D, suitable diameter of the shaft. Now, we know this relation, power transmitted is equal to 2 pi n, that is my rpn, and length, that is the change in length, into the torque, that is mean torque. Because n is given here in minutes, I will put 2 pi n by 60, right. I am talking about T mean here, which means the power that is there 100 kilowatts, which is equal to 100 into 10 raised to power 3 watts, which means using this relationship here, I will try to find T mean. Power is given 100 into 10 raised to power 3 is equal to 2 pi, value of n is 160 by 60 into T mean, which gives me the value of T mean as 5966.6 Newton meter. This is the mean torque. Now, maximum torque transmitted is equal to 1.25 into T mean is equal to 1.25 into 5966.6 is equal to 7458 Newton meter. Now we know maximum torque is equal to pi by 16 tau d cube. Tau max is equal to pi by 16 into tau into, that is volume here, volume into the shear stress. This is another relation. Now maximum torque is given to us. Maximum torque is 7458. Other dimensions are all in millimeters. I will also convert this into millimeter. It is 7458 into 10 raised to power 3 is equal to pi by 16 into value of tau is given already 70 newtons per millimeter square. Everything is in millimeters into d cube. This gives me d cube is equal to 7458 into 10 raised to power 3 into 16 by pi into 70, which is equal to 542.4 into 10 raised to power 3 d cube. This gives me the value of d, which is asked in the question. The suitable diameter is 81.5 millimeters. This is our answer. So these were a few numerical statements that we are discussing in static and fatigue loading. Another problem statement is there that I will also leave for you to do. It is given shaft is transmitting 97.5 kilowatts at 180 rpm. If the allowable shear stress in the material is 60 megapascal, find the suitable diameter of the shaft. The shaft is not to twist more than 1 degree in length of 3 meters. Take C here as 80 gigapascal. We have been given the value of C here, which is the constant of proportionality or modulus of rigidity. Now, in this numerical statement, you will go around and find the value of T, torque. The given value is already here. You will find torque. From the torque, then you will try to consider the strength of the shaft using the similar relation that is given above. You will find the value of D, and considering the stiffness of the shaft, you will use the relation J, this polar moment of inertia is equal to pi by 32 d power 4. Along with this, you will use another relation, that is T by J is equal to C into theta by L. So here J is your polar moment of inertia and T you know is torque, D is your dia, C you know it is modulus of rigidity, theta is the angle at which the twist is there, that you can calculate because theta is 1 degree here, theta is equal to 1 degree. To convert this into radians, this is equal to pi by 180. This is equal to 0.0174 radians. Right? So use these relations to find the value of asked missing parameter, that is suitable diameter of the shaft. So these are two relationships that you will use. One is considering the strength of the shaft. This is for strength, right? Also it is given stiffness of the shaft because twist angle is given. Right? You will find it is not only D, you call it D1 and D2. Both you need to find. D1 is considering strength, D2 is considering stiffness. You will find the values and try to compare that with the answer that I gave it to you. One last problem statement that we will take today is about this figure that is given. Here it is given a beam of uniform rectangular cross section is fixed at one end and carries an electric motor weighing 400 Newton. There is an electric motor here. It is fixed here at this end. Not at a distance of 300 millimeter from this fixed end. This distance is given 300 millimeters. The maximum bending stress in the beam is 40 megapascal. That is also given. Find the width and depth of the beam if depth is twice that of width. It has been given that depth is twice that of width. That is this h and b is given. We have been given this h is equal to 2 times of b. Let us quickly try to see the things. We have been given a weight of 400 newtons. The length is 300 millimeters and it is telling that 40 megapascal of bending stress is there. That is sigma b is 40 megapascals, which is equal to 40 newtons per millimeter square. H is equal to 2b is one relation that we will use. Depth is 2 times of the width. Now, let us use the relations which we have discussed in the lecture on bending moment. Now we know section modulus Z is equal to B into H square by 6, right? So here we know value of H is 2B, so I'll put it as B into 2B square by 6, which gives me B cube. 2 square is 4, 4 by 6 is 2 by 3. This is 2 by 3 B cube, millimeter cube. Now bending moment or maximum bending moment where? At the fixed end. This is denoted by M is equal to weight into length, that is 400 into 300. Directly it is Newton and millimeter. So this is equal to 4 3s are 12. 12 into 10 raised to power 4 Newton millimeter. Now we know bending stress that is sigma b. This is equal to bending moment per unit section modulus, that is m by z, which means bending stress is given here. 40 is equal to m by z. M is 12 into 10 raised to power 4 and z is 2b cube by 3. Right? There's only one unknown here, that is b, bending stress. This value we can calculate from here. So which gives me b cube is equal to 12 into 10 raised to power 4. This 3 goes above, into 3 is divided by 2 and 40 comes down here. 40, this is equal to 16.5 millimeters. So this is my value of b, right? This is your dimension b that is asked. That is, we now know width is 16.5 millimeters and depth is equal to 2b is equal to 2 into 16.5, which gives me depth is equal to 33 mm. These are a few numericals or problem statements that I have discussed in relation to the topics of hardness, toughness, or static and fatigue loading and critical loads. Also, a bending moment numerical is also discussed. I will further talk about some problem statements in the stresses in cylinders, something on buckling of columns and Mohr circle in the next part of tutorial. Thank you.